about computing propositional quantifiers by Hugo, Férée, and some. So they should appear on the screen. So the floor is yours, Hugo.
Yep, thank you. I hope you hear me well. Well, first, thank you for allowing us to participate in remotely, including talks, which is quite nice for many reasons. So this is joint work with Sam Van Hol, who should be online as well. And the point of this talk is to present a formalization of something called Pitt's theorem, which is a result about intuitionistic propositional logic. And one way to see it is to the ability to interpret propositional quantifiers in propositional intuitionistic logic. So what we get here are, well, first a Coq proof of that correctness result. And so an OCaml program by extraction that computes propositional quantifiers. And we'll try to give you some insights on what we improved from the basic proof, as usual. So here we're in the context of propositional logic, and propositional formulas are just, and or implication bottom. And the question is, if you have a formula phi, which has a special variable p, you wonder what are the logical consequences of phi which do not contain p. So in classical logic, well, there is such a formula EP phi, which is a consequence of phi, which you can define simply by saying that, well, it's the disjunction of phi where you replace p with top and phi where you replace p with bottom, right? And moreover, any consequence of phi which doesn't contain p is also a consequence of EP phi. So this formula is the least consequence of phi which doesn't contain p. Right? And what's surprising is that, well, this construction doesn't hold for this formula here, doesn't satisfy this result for intuitionistic logic, but the result still holds. So there is still a formula EP phi which is the least consequence of phi which doesn't contain p. And dually, there's also a formula called AP phi, which is the least antecedent of phi, which doesn't contain p. Any formula theta which entails phi, it also entails AP phi. So this sounds rather technical, but one way to interpret this result is to see AP and EP as formulas realizing the second order propositional quantifiers forall and exist, right? A is forall, AP phi is forall P phi, and EP phi is exists P such that phi. Right, so this result says that you can interpret second order quantifiers within the propositional fragment, which doesn't have those quantifiers. Another way to see this theorem is that it's what we call uniform interpolation. And we obtained this corollary using something called the Craig non-uniform interpolation theorem. I'm not going to explain that right now. But the idea is that if you have two formulas, phi and psi, you can, such that phi entails psi, well, you can always find a formula in between them in the logic, which only uses the intersection of their variables. And the uniform part of this theorem is the fact that this formula only depends on phi, it doesn't depend on the second formula, right? This only depends on the set of variables you pick and not on the right-hand formula that you choose. All right, so there are two proofs of this theorem, two large set of proofs. There are syntactic proofs. The original one, we can call it syntactic. That is, we look at the formula phi, and by some rather involved induction, we're going to see that a bit later, you can build the formula. And the second one is a semantic proof. There's a few semantics proof around, but the downside is that they are not very constructive. They don't really build the formulas directly, and there's not even a bound. You can't even deduce a bound on the size of those formulas, which can be quite large. So we choose to implement to go on the constructive side and to implement the syntactic proof. So when you think propositional intuitionistic logic, you may think of Gansen calculus, LJ. But the issue with LJ is that it doesn't have an obvious terminating proof search. And one of the reasons is the left implication rule, which may replace a sequence with a formula here, like phi1 or phi2, with another one which might be larger. Right? Psi can be replaced with phi1, which may be larger. So the natural idea is to split this one rule into 4 sub-rules, where you look at what phi1 looks like. So whether phi1 is a conjunction, a disjunction, an arrow, or a variable. And this way you get rules that look like this middle one here, such that, well, the formula you get at the top is somewhat smaller than the one on the bottom. The second point is that to avoid contraction, which also is problematic for termination, you use multisets on the left of a sequence. So the result is in calculus called G4IP in the literature, and sometimes it's also called LJT, but that is sometimes confusing. So we use this calculus G4IP, which has the property that, well, it has a terminating proof search by construction. It admits contraction and contamination, etc., and it's a sound and complete calculus for intuitionistic logic. Okay, so what does it look like in COG? Very quickly to give you a glimpse. So throughout the development, we try to stay as close as possible to the original definitions and theorems, and we made, well, a lot of the work is about keeping things close to the original definitions and theorems, well, proofs. And so you can see, for example, the imp and rule, which I'm going to use as an example later, looks like this. And you should only notice that, well, the bullet here is the construction that adds a formula to a multiset, right? And you see that this rule is really replacing a sequence with a given formula by another formula. All right, so this is just an excerpt of the definition. All right, so how do we build those formulas EP and AP? Recall that EP should be the strongest possible P3 formula. That's a consequence of phi, and conversely, AP should be the weakest precondition antecedent of phi, which doesn't have P. And they are defined this way by Pitts. EP is a conjunction, AP is a disjunction. And, well, first, for the induction to work, we need to generalize a bit, and we need to not work with formulas, but with, actually sequence, or, a multiset delta of formulas and a formula phi. So the question is, what are those sets curly E and curly A built, how they are built? So in Pitt's definition, which is very, mathematical and not very operational, it's not a program really, and the whole difficulty of the work is to translate that sort of definition into a program, a COG program. It looks like this. It says that whenever the multiset of formulas delta matches one of those rules, and this is just an excerpt, well, you should add to the set E of something, or a formula you coding. So recall we are defining E as a conjunction of formulas in the set curly E, and you add a formula like this in curly E by calling E on itself. Some things you should know about these rules. So, for example, rule E6 illustrates the left implication rule I showed earlier. So you replaced an implication with an and on the left-hand side with a double implication. You are actually defining
Hugo,
this.
you have been lost for a bit. Could you maybe go back like half a minute?
Oh, okay, sorry. Can you tell me when I was stopped? So yeah, I'm gonna try to go back a bit. So we're defining E as a conjunction of formulas like on the right-hand side, and for each formula in delta matching, the left-hand side, you should add one of those formulas on the right, which does an inductive call to E and A. So the E and A are defined by mutual induction, and yes. E and A are defined by mutual induction, and you're calling it on potentially formulas that are smaller for some weight, but you may replace one formula with two smaller formulas. Okay, let me be a bit more precise. So we define a weight function on formulas. Basically, and weighs like 3, implication is 1, and conjunction is 2, or something like that. And this induces a well-founded order on formulas. And by the Dershowitz-Mana theorem, we get a well-founded order on multisets of formulas. And what you need to observe is that in the previous table, all the calls to E and A are smaller for this multiset ordering. So our job is to convince Cog that this is actually the case, and that this whole mutual induction using a multiset ordering is actually well founded. So that table I showed you earlier is translated into a function that looks like this. If you give me delta and phi, so this is a Cog definition, but if you don't read Cog, that should be fine. If you give me delta and phi, I can build one element of the conjunction, which should be the thing on the bottom. So this is a big match, which matches a formula that you give in argument that is in delta. And if it matches one left-hand side of the rule, you should produce the right-hand side, which depends on E and A that you obtain by the induction hypothesis. So the induction hypothesis is here, and it says that I can build E and A as long as you provide me with inputs that are smaller for the multiset ordering. Okay, this is just a taste of the definition. And you should notice also the underscores here that are provided by the program scheme. And they are actually they actually ensure that you only call E and A on inputs that are smaller for the multiset ordering. So typically you have proof obligations of that form. If you have that formula in delta, then you should prove that replacing that formula with those two is still satisfies the multiset ordering. So this is all done automatically. And then the main definition is about mapping these rule sets to each element of delta. So this looks like a simple map function, but it really is a dependent map function. That is a map function that applies a function to each element of delta, but which itself depends on delta, because we need to know that the element you're mapping the function to belongs to delta. So this is a technical point, but which was crucial in the proof, and that's the kind of thing that do not need to be spelled out in a paper proof. So the main definition looks like this. It basically looks like the definition in the paper. E and A are defined, simultaneously using a well-founded order. That's the multiset ordering. And the first one is a big conjunction. The second one is a big disjunction, which are both obtained by mapping some some function, some dependent function on the elements of delta. A remark now, we realized after the fact, after implementing the proof, that the Pitts proof is a bit of a hammer. It's a bit too much for this construction, because it relies on the multiset ordering, which doesn't help us understand the complexity of the formula we build, nor the time complexity of doing this computation, which is at least exponential. And we realized that, because each formula in the construction is only replaced by two smaller formulas, we only make induction calls on at most two more formulas. Well, this weight function should work as well. So this is not formalized yet, but this weight function, it should also be compatible with the construction we made. And it should provide an explicit bound on the complexity of the formula we build, and on the time complexity of this whole construction. So what does the correctness proof look like? Well, it's a lot of the work is hidden really to make the whole proof easy, the main proof easy and nice to handle. And there's a lot of tactics that depend on Iris std++ library, namely the multiset side, which help us write intuitionistic proofs very easily and almost naturally. The proof also relies implicitly on admissibility of lots of standard rules of intuitionistic logic, like weakening, contraction, some special cut rules, all from Dikoff and Negri. And that's a non-trivial part of the development, and that's actually reusable, so it's a nice byproduct of the development. Now the easy part of the main proof is to prove that our formulas do not use P, that there are consequences and antecedent of phi. And the hard part is to prove that they are respectively minimal and maximal. So the idea of the proof is that this is a big induction on the proof of a sequence, and there's a case distinction according to the last rule applied. And basically every line in Pitt's table corresponds to that last rule that is applied. So that main bit takes only 200 lines of code, but it really is the fruit of simplifying things in beforehand. And the total development is only a few thousand lines of code, but we try to factorize a lot of stuff. So this is the main theorem. It looks like just what I spelled out at the beginning. So for every formula, we can build a consequence of that formula that doesn't contain P, and such that any consequence of that formula is also a consequence of that formula, of EP5, and conversely for A. So now that we have the Coq proof, we can actually use the Coq extraction mechanism. And this way we can obtain an OCaml program which computes, well, correct by construction, which can compose those two formulas, the forall P phi and exist P phi. And you can experiment with it, and quickly you realize that this construction has a kind of worst case when you have a lot of intricated arrows. So if you get the formula phi n, which is n arrows, and the formula you want to you put the variable you want to eliminate on the left-hand side, really deeply at the deepest, then you obtain a formula which has a very large, quantifiers. So EP phi and AP phi are pretty large, and they grow exponentially. So this table sums it up. So if you have only, like, say, 5 arrows, already the size of the interpolant is a few thousand, weighs a few thousands. So one point I didn't mention earlier is that we implemented the original proof, and here you see the numbers for the original proof, the size of the formulas you build for E and A. But we also did some optimizations, meaning that when we build in the interpolant, or the propositional quantifier, we use some admissible rules of the logic, like if you have bottom and something, you can simplify it. So we did some pruning here and obtained smaller interpolants than the original proof, which is something the original author of the proof didn't worry about. So there might be a lot more work to do here to simplify the interpolant, but it should be exponential in size anyway on that example. Okay, to summarize, so there's room now to potentially more experimentation now that we have some actually executable tool. The main point maybe for the future is to generalize this theorem to other logics. So this theorem actually holds for other logics than intuitionistic propositional logic, and we would like to get the essence, like the key assumptions that make this theorem work on many logics. And finally, we'd like to understand the computational interpretation of that theorem, seeing that logic on the computational side. And well, thank you for your attention, and I'm happy to take questions now.
Thank you very much for the talk. We have time for one quick question.
What kind of use cases do you have for this proof?
I'm not sure about that. I'm guessing there are a few applications in proof assistance. I think that there's a use of this theorem in some coq tactics. I don't recall which one. Maybe Sam in the chat can help me out. Because finding the smallest consequence of a formula helps you. Well, it can. I think you can use it to do some automation tactics to see what you can conclude from that formula. If that's clear.
Okay.